So we're going to kick off this next session with Peter and Michael from ESET. So some really interesting research about rich headers. So we're going to be talking about rich headers and leveraging the mysterious artifacts of the PE format.
Okay, hello, welcome to our session. We would like to deliver this talk. We did this research for several months, so let us start it. The outline of our talk is as follows. We start with a brief description of rich headers, briefly RH, just to be safe that we are on the same side. And then we show the tooling, like how we design the database that stores the rich headers data and which tools we kind of use to leverage this piece of information. And finally, we will conclude with lessons that we learned, like tracking the feeds, delivering stuff based on rich headers. So, rich headers were implemented in Visual Studio 1997, Service Pack 3. So it's already 22 years ago. It's a kind of ancient structure. And Microsoft has never announced and never documented or even allowed developers to opt this feature out. So perhaps this kind of supports our choice of the mysterious word in the title. Let's briefly mention the main events connected with rich headers. As we said already, introduced 22 years ago. And in 2004, 2010, researchers started to ask questions, what this piece of data mean and how it could be interpreted and so they tried to collect some basic information about this structure. As you see, times went on and there weren't that many pieces of research focusing on this data. But recently it got hyped more because the first academic paper from 2017 came by Webster and his colleagues. They chose, I believe, 4 APT families and they did some clustering on these families, so they did some kind of initial research about how to leverage this data. Then a great team published an interesting paper where they kind of described how one APT actor borrowed or copied or stole the whole rich headers blob from another APT actor, just to be some kind of, just to use it as a false flag. And we did our research last year about Lazarus. We tried to cluster the huge toolset of Lazarus based on rich headers data, basically linker version, major one. But that was kind of motivation. Why take a look at this structure? And recently, the rich headers got even more hyped because Maxim Dubik wanted his SENSE certification, so he did research on this. Again, he chose some kind of not that huge data set and cluster it based on rich headers data. And there would be Cyber Defense Summit of FireEye. So really, this topic is getting hype. So what is a rich headers structure? It is in the PE header of executables coming from Visual Studios. So the structure is produced by Microsoft Linker. And this is overlooked, as we briefly mentioned before. And it is just a blob of data starting with some header, double word, magic value, you name it. And there's a triples of information. Triples consisting of product ID, build number, and counts. The first 2 values represent the building environment that binary came from. And the last value represents the magnitude of the project. Yeah, this is what we say. The structure itself is not plain. It's XOR encrypted. And the XOR is stored in the blob of data. But there is a formula that would help you to count the value. So there are 2 ways how to get the value of XOR key. And this is how it looks in the binary. And if you kind of decrypt it, it's in the plain form on the right. So in Microsoft 2000, source code leaked. So researchers tried to get information about rich headers from this data. And actually, ProdID is the original name by the developers of Microsoft. And that is like the piece of code from the leakage on the left. And on the right, there is kind of IDA hex race decompilation, how it looks in the recent Visual Studio 2019. So one may ask, how often is this data included in a binary? So if you consider any file, it is roughly between 66 to 71% of executables that contain rich headers. And if you take a look at a malicious set, like this malicious set represents really not just some kind of random data. This is like the set that contains representative of malware executables since, I don't know, 2004, or maybe even longer. And in that case, roughly 73% of binaries contain this information. 15% of binaries were coming from Visual Studios, but omitted this information. This could be caused by developers patching their Microsoft linker file or some usage of protectors, packers that kind of replace the data. And the rest is like not containing at all and not Visual Studio executables. Rich headers starts at some offset. Basically, the offset is a function of or depends on DOS stub. So you know this can't be run in a DOS mode. It's at some length. This is the majority of cases, 99%. But if the guys chose some different DOS stub, it also pushes the start of rich headers forward. So there is a variety of offsets that could legitimately represent rich headers beginning. And actually, one needs to think about this if he wants to parse rich headers. So our motivation was clear. If you have a binary containing rich headers and you want some kind of similarity to get more binaries of the same nature. So we were thinking about how to get these levels of similarities, and we came up with this hierarchy. We don't say this is like the unique option. Perhaps there are better options, but for the start, we were happy with these at least 5 levels. Let's go one after another. So level 0, of course, identical rich headers. So you have some rich headers, and you want to get all files from your feeds that contains the same rich header. We were really happy about this because Temida Enigma VM protected files actually didn't alter the information. So, and it was really without any dynamic analysis, you were able to, if you have a kind of unprotected files and you have protected file and those rich headers match, you have a really quick hint that these binaries are the same. Just they have a different form. We did a kind of attribution of predator stealer between unprotected and protected ones, and NukeSped, which is Lazarus toolset that we track a lot. And sometimes rich headers got faked or copied or so, and it was the infamous case of Olympic Destroyer. People talk about this as it was a false flag, but from my point of view, as the rich headers were a little bit mysterious structure, it was Easter egg, not really a false flag. I know that you are familiar with the case. When also we've seen cases that explorer.exe and its rich headers were copied to malicious file. And actually, you can quickly identify some stubs using the complete rich headers block of data. Level 1, which strictly generalizes, the first one is that the two files have the identical XOR key. And we found this useful in cases of malware packers when obviously malware packer was kind of a stub, and the identical XOR key were kind of clustering many executables of the same nature. And also, we found you could easily identify stubs, Visual Basic files, ANSYS installers, and so on. The next level, unsorted pair of product ID plus build number. So this strictly generalizes the previous one, and we found, okay, CoinMiner is never a small project. It is a large project, but we found out that sometimes the number of imports varied. So obviously the previous two similarities couldn't cluster this into one group. So we just ignored count number, and we were really happy that CoinMiner was really clustered well using this level of similarity. The same was like binaries distributed by Tirodo. You can see a lot of values varied, but if you kind of omitted these values, you could get a nice cluster. But we realized that it's not that easy. Sometimes Microsoft Linker didn't follow the order of product IDs, so we did this another level that we sorted it by the product ID. And in this case, we were able to cluster well this NuxPad stuff and gray energy files. Okay, what is interesting about this structure is that it represents values like number of imports, exports, resources, and these information are kind of doubled in the PE header. So you can kind of find mismatches or values that are not corresponding to each other based on these two pieces of information. So these RH anomalies we were thinking about, it could be a good base for heuristics, but we didn't put focus at it at this time. But it could lead really to a quick malware verdict of a file. So let's move to the second part. A small team of developers or even a single man show, one dedicated man could build the whole infrastructure required to leverage this structure. And now I put the words to Michal, who would continue with tooling.
Mm-hmm. Thanks, Peter. So I want now to tell you something about our internal tools that we've made for this project. So let's first start with some technologies that we used for the whole infrastructure. We, of course, used Visual Studio to code the whole thing. The backend is written in C++. The front-end is mostly C#. And we used MySQL for the database storage, and we also try to leverage the YARA tool and incorporate it into the tool set, so it's there too. So let's first talk about the database. It's meant to store all the related metadata. In our case, it stores data from multiple live feeds that we process in real time as the files come in, and as well as infected and clean data sets that we can use to compare the unknown file against. And relating the live feeds, we process about 240,000 files, new files per day. So it's decent traffic. Here's the database design. it's a quite simple database. There's a main table called file, which holds all the file-related information. And for each file, there's 1 to n rich records, and each rich record represents the rich header triple, which holds the ProdID, build number, and count information. So each file can have multiple rich records. So it's quite simple design. Now, the way we fill the database is with our backend tool called PERichFinder, which parses the P files and stores them into the database. We try to keep the high performance in mind, since it's meant to process lots of data, so it's all written in C++, and we try to avoid to use lots of third-party libraries. So it's like we try to use as much low-level API as possible to maximize the performance. And it supports multiple operation modes, so it's used for the live-feed processing, which is like real time, and it runs the whole day, like constantly processing new files. And then it also supports on-demand file system scan when you have like a folder with set of files that you want to put into the database, create some cluster. You can just use that as well. There's no screenshot of the tool since it's a command line tool, so just, yeah. Then the front-end part, we call it PERichFinder, or the client. It's a .NET applications, since performance is not that important here. It's meant to look up similar files in the reader database. So when you have like some new unknown file that you don't know anything about, you just use the tool to see if there's like some similar files in the database already, and it could lead to some quick attribution. And it's, yeah, so it's used to find the commonalities among a set of files. And of course, we also use it to create notification, and it supports export to rules, so we can both like so we can use the tool to create a rule that will be used in other applications that will scan for the same set of rules. And last but not least, we also contributed to the original YARA project by Aristotle, since their implementation of regenerers was not complete. So we tried to extend it, and now we feel like it's equivalent to our SQL rules, that it supports complete regener lookup. And now I'll give the word back to Peter, who will tell you how to leverage the client-side tool.
Yeah. So let's talk about the client. So you can develop your client as you wish, but this is just a hint how to do it. So it is a client that could be run on those files as well as on a folder. And if you run it on a file, you can see on the left there's the list of triples included in the rich headers blob of data, and you can see the database that's implicitly like set for the lookup, and here are the levels of the hierarchy of similarities that you could be interested in, and basically that's it. And perhaps more interestingly, you could run it on a folder, and in that case, it took kind of a union. It took union of ranges of ProdIDs that are like in the intersection of the files contained in the folder, and you can manipulate with this data to create the rule, to create the SQL rule that queries the database, or you could create a rule that queries not queries but scan file on a file system based on a YARA project. And yeah, this is the union or intersection of information. And actually, this is an artificial example. We have one cluster of files. I believe it is apt37 downloaders or something like that. And we put one file that was not related, that was not coming from the same environment. And we developed it in a way that if you click on the product ID triple and the one that represents anomaly in the folder, you could just press delete, and now you just can manipulate with the rest of the data, which is really like homogeneous now and represents really the cluster coming from the same environment. And you could just pick those triples and make the conjunction of these triples would be queried to the database, and you see it covers several files. And if you query it on a clean set, 0 hit. So this is a really good rule that you could track your data, your favorite APT actor. And we mentioned we have two types of rules, SQL and YARA rules. SQL rules queries the database. They look like this. It is really not like comfortable to write it by hand, so the client does the job for yourself. And you also want to have the YARA rule that it could be like executed on a file. You could be like, you could wonder if this file is already flagged by one of your rules. So YARA is a really good scanner here. And we, of course, need one-to-one correspondence between SQL rules and YARA rules. And at this moment, in those months that passed, we wrote about 200 rules, mostly APT toolsets. And now I would like to say something about what we learned by tracking these 200 rules. And at first we were worried that those triples wouldn't generate the space that would be interesting enough. That those triples would be like kind of rough. That malicious files and clean files would collapse into one big cluster without any useful information. But we were lucky, or not lucky, we were kind of surprised that the space is more granular than we thought from the beginning. And this makes sense because imagine the structure was introduced in 1997, and more and more Visual Studios are coming, so there are more and more building environments like producing Visual Studio executables, and so the space is granular enough for our purposes, and actually it is rich indeed. The space generated by triples of ProdID and the information stored in rich headers is rich enough for tracking and reasonably distinguish between malicious and clean files. So let's move to the examples. First generally, disadvantages, advantages. So it is a small piece of information, so it is easily stored and quickly accessed. This is a really good thing. And basically, malicious projects, not considering like coin miners and projects that incorporate big open SSL libraries, are basically of small size. So this is something that put heuristics on the side of maliciousness. And when we wanted to write a rule, we always wanted to cover multi-stage attacks. So to cover with one single rule, dropper as well as the payload, or 32-bit variant as well as 64-bit variant. And this was possible. Yes, and also creation of anomalies could lead to a quick malware verdict, but we didn't do that much in our research. So the disadvantages, of course, rule need to exist, so you don't get any proactivity. You need to learn about your APT toolset and to create rules and to track them. You need to do this work manually. And tracking is lost with any update of Visual Studio because the build number changes, and also with the large refactoring of a malicious project. And what we learned, okay, there's a quotation for each of the 200 rules already exists the false positive, but this is not that negative statement, of course, because this is a really small piece of information. You can't expect that you could detect families based on this. But the nature of false positives are kind of rare. It was various proof of concepts, tools from specialized software. When we were lucky and the certificate was present, so we could at least identify where the binary came from. But also there are many small components of projects of unknown origin and functionality. And what was curious enough, that one rule could cover more unrelated malware families that we experienced too. So let's start with the examples. As we told already, the motivation was in our research of APT Lazarus group and its toolset. It is really huge, so we were really like grasping at straws to find some relations. We did the paper last year, and we found out that at least two major groups were present. One was using Visual Studio 98 and 2010, and the second group was using Visual Studio 2010 exclusively. But of course, we also found many anomalies. If you are interested in just check the paper. Okay, this is another example. This is a conjunction of ranges, like object count, CPP objects, usage of assembly at a certain version, and number of imports, and so on. And this rule is like not great to cover malicious projects exclusively, but it could cover industrial binaries and hexagrammar binaries at the same time. I'm not saying that there isn't any other projects that are flagged by this conjunction of rules, but at least the conclusion is that the guys were using the same building environment, and the project was roughly of the same size. And actually, these two families are connected, linked in the paper published on Village Security. Another example, I encountered a strange binary, happynewear.exe. It contained character strings like scout, scout, scout. It contains very familiar methods of dynamic calls. And actually, it was for me obvious, wow, this is a hacking team binary. And actually, it was not flagged by our detection engineers as a hacking team. So I told them, hey, guys, you did a poor job. This is hacking team, right? So please reclass the detection. Yeah? But they told me, hey, my friend, be careful. It is not hacking team. It is just a downloader incorporating source code that was leaked, of course, and those strings are unreferenced. This is just a downloader. It's not hacking team, and we won't reclass it. And okay, I took a more detailed look, and I realized, okay, this is downloaders for APT37. But actually, when I rescanned the file, I realized that my YARA rule was flagging the file as APT37. The building environment, the magnitude of project was really related to the binaries attributed to APT37. So for me, wow, this is really cool that first, if you take a look at character strings, you could think, okay, this is hacking team. But if you take a look at the building environment, you could say, okay, perhaps this is not, and it could be something else. And another examples, okay, suspicious file, export name, LCR PSD new.dll, and using similarity levels, I found out, okay, this is really, really close to a file called loadcrypt.psd.dll. This DLL is really small. It's just a tiny piece of code. It's a loader, no data, so no quick attribution. And but the file that was similar to the original one is already flagged as pre-conca. So the conclusion was, wow, this is a new campaign of Operation Groundbait. And so let's summarize it. I believe we have just time for the summary. 3 points. Rich headers are implemented 22 years ago. Microsoft not offering any option to opt it out, not documented, and never announced. So it's mysterious. I believe a small team of developers or even one single dedicated man could build the whole infrastructure behind this project. So you could get kind of a lot of information for your APT tracking for a little effort. And rich headers is a static feature that can reasonably distinguish malicious projects from the clean ones. And I think this is where I stop. So if you have any questions, I don't think we have time. Yes.
Yeah, I don't think we have any time for questions. Thank you very much for the talk. It was really good.